The thing says we're live. Hey guys, what's going on? Memes here, and today we're bringing you a very special presentation titled Radical Powers by Physics Monastery Fractal Faculty Rick DeWitt here. Say hello to the folks, Rick, and why don't you give us a little bit of a preface about what we're going to be delving into?
Hello, folks. My name is Rick DeWitt. I'm a mad scientist. I've been working on gravity and other stuff for a while. And I was seeing memes of destruction go into some stuff about alpha. And I had an interesting insight that I wanted to share with him. And so we're just going to kind of go through that. And we're going to learn about the Planck units and how they relate to each other. So this is called radical powers because we're going to make a table of powers, and across the column headers are all going to be radicals. A radical is a square root sign. So when we say radical h bar, we're going to have h bar, but it's underneath square root. A radical c is going to be speed of light under square root sign. So all of these things are going to be radicals, and then we're going to look at all the different kinds of units that are described in the Planck scale. And we're going to make a table, and the table is just going to have a bunch of integers in it. So a blank square on the table, we just treat as 0. It just means it just doesn't matter. And so we're just going to fill in the non-zero integer powers of each of these different dimensions. So I'm going to ask Memes of Destruction to head to the whiteboard. And if he could make his screen large, all perfect. Right. Cool. And then so leave a little space at the top. Leave the top row open. We'll do the column headers after the row headers.
Okay. So
the row headers are density, force, acceleration, and energy. Let's start with those.
So these are going to be the rows?
Yeah, there's going to, just do rows a little lower.
Yeah.
Yeah, okay. So the first one is density.
Okay. Do we need room for 18 here?
Yeah. Okay. So
I will adjust my penmanship accordingly.
Yeah.
Okay. You got density.
Force.
Okay.
Acceleration. Energy. Temperature. Frequency. Momentum. Mass. I think I'm going to skip a few rows here. The next few rows would be speed, h bar, gravity, and alpha. We're just going to do alpha because the others are going to be trivial. So just do alpha as your next row.
Gotcha.
Charge. Length. Time. Area. Volume.
Is that the last one?
That's the last one.
Okay. All right. Thank you. I was going to run out of room.
Yeah, that's why I'm skipping those rows.
We don't want it to be incomplete, but as long as we can convey the precipice that you're laying out for your upcoming work, that
can you move your screen down just a little tiny bit? Memes of Destruction. There you are. Perfect. Yep. All right, now we're going to do column headers. Okay.
Yep.
The first column, I'm just going to ask you to put an equal sign and leave a little space,
Okay.
and then that'll be the symbol
Okay.
for all these things. But I think if you could draw that vertical line,
Yeah.
and the next vertical line, really nice. And then radical C.
Radical C. All right.
Radical C.
All right. We're getting radical here. All right.
And then a line, vertical line, radical H bar.
I like where this is going.
Radical capital G.
G.
The next one is radical Boltzmann constant. So it's
Right.
K sub B.
Yeah. Radical K sub B. Okay.
The next one is radical Coulomb constant.
That's big C.
It's K sub E. So it's the electric.
Okay. Oh, electric constant. All right.
K sub E. It's the one that appears in Coulomb's law.
That's big K sub E, correct?
Yeah, it's I think it's a lowercase K,
Okay.
lowercase E.
All right. Gotcha. K sub E. All right.
Yeah.
You got it.
That's the electric constant.
Yep.
And then the next one is radical charge of the electron. So it's radical lowercase e. And I kind of want to just do an E sub little e, or little e sub little e, so that people know that this is not Euler's constant or Euler's constant or Bueller's constant.
Euler. I love that clip. It's like, oh, we were all saying it right because it's the German. And that's
so lowercase e.
Okay, so lowercase. I think it's these are all constants, so I think we'll explain. Okay,
that's right.
I'll put parentheses. The electron.
Yeah, electron.
There we go. When in doubt, add a footnote.
Okay. Ready for your horizontal line under the constants, under the radicals.
Oh, yeah. All right. Let's get this here.
Okay.
All right. We've got them.
Now, if we want to describe, let's see. All right. So should we name the constants and do that equal sign thing, Colin? Or just dive right into the numbers?
Let's go with what it is, because I want to make sure I understand before I get confused.
Okay. So density, the symbol for that is rho sub uppercase P.
Okay, so it's going to be rho, which is a funky little p, and then uppercase P.
Yeah, but it's the subscript uppercase. Yeah, there you are.
Okay.
Yes, that's all fine. Force is uppercase F sub uppercase P.
Okay.
Acceleration is lowercase a sub uppercase P.
Yeah.
Energy is uppercase E sub uppercase P.
Yeah.
Temperature is uppercase T sub uppercase P.
Yeah.
Frequency is lowercase f sub uppercase P.
Yeah.
Momentum is lowercase m, uppercase P, subscript, and then that's multiplied by c.
Okay.
The speed of light.
Yeah.
Yeah. Planck mass is it's lowercase m, uppercase P.
Yep.
Okay, now we're going to switch to subscripts that have lowercase p.
Yeah.
The first one of those is charge, which is lowercase q sub p. And then we have length is, oh, that's right, alpha. I missed that. Alpha is just the Greek letter alpha.
Alpha. Yeah.
Yeah. And then the next one below is length. So that's lowercase l sub p. And then time is t sub p. And then area is L squared sub P, and volume is L cubed sub P.
And then cubed.
There we are. Okay.
Let me draw the, finish drawing the line, because otherwise I'll be all over the place. Okay.
You betcha.
Okay. We're making it sharp.
I'm just so happy you're doing this. This is awesome.
No, this is helping me because I'm learning the programming language of the Wolfram language, and finally, after like a couple of years and actually sitting down and spending time, yeah, it's actually starting to make sense. It's like, oh my God, I think I'm on the cusp, and I might actually be able to, I don't know, maybe do something useful at the Wolfram Summer School. We'll see. Yeah. Almost. More. Just enough space.
Okay.
All right.
So let's start out at the top of the screen.
Okay.
We'll do density first. Now in that blank area to your right,
Okay.
to the
This one?
right hand side of the table, like all the way over that blank area right there.
Okay.
So I want you to write down this expression that rho sub p equals c to the 5th power divided by over h bar g squared. You can write h bar with the h slash.
Oh yeah, I'm so used to typing the Wolfram alpha.
That's right.
It's my even Thad's like, you can write it just with a little hat.
Yeah.
So yes, that's correct. I have to think about it to do that. All right, got it.
Okay, so now that you see that expression c to the 5th over h bar g squared,
let me move this down. Just
radical c. Yeah, there you are.
Okay, yeah. I just want to get this correct. So big P equals a c to the 5th over h bar big G squared. Okay, got it.
Okay, so you see that c to the 5th. How many radical c's does it take to multiply together to get c to the 5th power?
Take 10.
Very good. Put a 10 in the box over in your chart.
Gotcha. All right.
That's a 10. How many h bars in the denominator does it take to make, how many radical h's are there in density?
2.
Okay, put a 2 down there.
Okay.
What's wrong with that?
What is wrong with this? 2 radical h bars. That's a good question. Wait, oh. Is it because h bar it's a mass area rate. So it's mass.
You don't have to think about it.
Okay, I don't know.
You're thinking about it.
All right.
How do you notice something different about the c to the 5th and the h bar when you look at it?
Oh, it's a magnitude of 5 difference.
You got the 2 right, but there's something you got to do to the 2. Because it's in the denominator.
Oh, -2.
-2.
Oh, okay.
So now you've got this g squared.
Okay. So that would be -4.
There you go.
Okay.
You're off and running. So the whole table comes out like this.
Oh. Okay.
So now the next one is Planck force, which is c to the 4th over g. Okay. So you just, if you want to erase, that's fine. You can just keep going.
Oh, no. I want this. No,
You
You
started
betcha.
telling me about this once. I was on minimal sleep. I have it on a note somewhere on my phone, and I never got around to it. I'm like, okay, this is an interesting thing. It's something. I'm like, there was a question. The radical threw me off. Okay, so
Force
that's
is c to the fourth over g.
the fourth over G. So in this case, this will be, okay, so we have 8 over here, and that's in the denominator, so that'd be 2 radical G's, or excuse me, -2, minus 2 G's.
You
Okay, I'll
are
take
off and
square
running.
4. All right, and then acceleration. All right, so
Acceleration is radical c to the 7th over h bar g.
H bar G. All right, so we do 7. So that would be a total of 14.
Except now it's a radical. That acceleration is underneath a square root sign.
Oh, okay. The
The
whole
whole
thing?
thing.
Yeah, okay, that sounds right. All right. So then that would just be 7.
There you go.
Okay. 7. And then it would be, right, so -1. That's 1. And that would be -1 for G. Okay.
Yeah.
We got energy.
Energy, I think we'll just start writing down formulas. So energy is E sub P equals everything under the radical,
Yeah.
H bar C to the 5th over G.
Oh, and again. H bar C to the 5th over big G, or?
Yes.
Okay, H bar over big G. Okay. So
temperature is the same thing as energy.
Yeah.
But there's a K squared B in the denominator.
Okay. Yeah. It is. That would be everything radical. H bar C to the 5th, big G, and then a small K.
K squared sub
Yep.
B.
K sub B. Yep. Okay.
Frequency, lowercase f sub P is everything under the radical C to the 5th over H bar G.
Over H bar G. Yep.
Momentum is everything under the radical H bar C cubed over G.
Cubed over G, all radical. Okay.
Mass is everything under the radical. All of these. Well, anyway.
Yeah.
Sorry.
The rest
Mass
of them
is everything under the radical H bar C over G.
Okay.
Alpha. I'm going to skip alpha for a little bit. We'll come back to alpha. We'll do charge.
Yep.
Is everything under the radical is 4 pi epsilon naught H bar C.
Not. Yeah.
Okay.
Is there like a 2 pi or something in there, or like 2
That's
times the square root? Okay, no. Okay. Oh, I see what you're
I
doing.
put it all underneath in my chart in my paper.
No, okay.
That's how I wrote it. So
yeah,
I'm not.
Okay.
Anyway, so length is everything under the radical H bar G over C cubed.
G over C cubed.
Time is H bar G over C to the 5th.
H bar over C to the 5th.
No, time is H bar G, and then that is over C to the 5th.
Okay, yeah, I remember.
Area, in my notes, I don't have it under the radical.
Okay.
This is outside the radical H bar G over C cubed. Then volume again is under the radical
Yeah.
h bar cubed g cubed over c to the 9th.
Can you say that one more time?
Volume is everything under the radical h bar cubed g cubed over c to the 9th.
Gotcha.
All right. Now go to town.
All right. Let's fill this in. All right. So we got acceleration. All right. So energy, this would be, all right. So we got one here. It's going to be, so it's going to be 5 radicals. We'll have there. 1 radical G. So that's up -1. -1. Okay. So now we get to temperature. So it's going to be 1 H bar, 1 radical, maybe 5 of those, and then -1 G, -1, -1 KB, negative
That's
1.
-2. The KB.
Oh, it's a KB squared. Okay, it's KB squared, correct?
KB squared in the denominator.
Okay, so -2. Gotcha. Okay, so -2. All right. So then we got frequency. That's going to be 5 of those radicals. 5 -1 H bar -1 -1 G -1 G MP H bar. So it's going to be 1 radical H bar, and then it's going to be -3 radicals, C radicals -3, blah blah blah, and then -1 G -1, and then we get blah 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 mass. Okay, so 1 radical H, 1 radical C. Radical
Momentum. Check radical C
Is,
for momentum. Do you have it in the denominator?
I have it. Oh, it's H bar. Oh, it's H bar. The C is in the numerator.
Yeah, momentum. Radical C is in the numerator, and in your chart you have a -3.
Okay, yeah. No, I had it in the wrong place. All right.
Okay.
Sure. All right. So that's gonna.
This is why I wanted to do like a live thing instead of like sending you an email.
Oh yeah. No, well, this is how you learn. You actually do it.
Yeah.
So okay, so we got
alpha. We'll get to.
Yeah, I might have a slight hunch. I don't know, but okay. So then -1 for G there. Okay, let's skip over that. So we have all right. Did we want to put epsilon naught on the table? Like, should that?
That's inside the electric constant. So the K sub E has an expression which is 1/4 pi epsilon naught.
Okay. So that would be 1.
So
go to charge, and that would be 1.
Yeah.
And then 1 radical C. Okay.
Let's see. Except under charge, root K sub E, there's a -1. That's a negative.
Okay.
We're just going to fix that up right here. So it's the charge is 1 over that. That's all.
Okay.
That the table's correct, I believe.
Okay, the table, I just want to make sure I have the right notation. So it should be radical 4 pi epsilon naught C, or is it 1/?
It's radical, everything under the radical 1/4 pi epsilon naught.
Gotcha. All right. Like this. Radical 1/4 pi epsilon naught C. So that would be okay, so C should be -1 too, correct?
In my chart, that should be a 1, and then there's 1 H radical is I think we miscopied on the charge expression because I don't write it the same way.
Okay. All right. No.
So rewriting charge again.
Okay.
In my notes, I have under the radical 4 pi epsilon naught h bar c. But that 4 pi epsilon naught really is in the denominator, because the way I write it in my chart, I'm actually doing my column title is radical 4 pi epsilon naught, just because I like to write it that way. So on your chart, you should have 1 radical c, 1 radical h, and negative radical k sub e.
Okay, gotcha. Okay, yeah, because you can rewrite it as, okay, so 1 radical c, 1 radical h bar, and then -1 radical k sub e.
That's it. All right. And then length is every, no, wait.
Yeah, I got you.
That's right, you're already on it.
No, I know how to. Yeah, no. The charge is one of those wonky ones because you can write it.
Yeah, that's why we're skipping alpha.
Yeah. Okay. So length would be all right. So 1 h bar minus. Hold on, wait. Okay, that's under the radical, so that would be -3, and then 1 radical g length, and then we've got time, which is okay. So it's going to be -5 for radical c. That's going to be 1 radical h bar, 1 radical g, and then we've got area, which is going to be 1 radical h bar, 1 radical g, and then wait, no, it's going to be 2 because that's not under the radical. Okay, so that's going to be 2 of those, so 2, and then it's going to be 2, and then that's going to be -6, so -6 of those, and then we're going to have okay, so 5 radical h bar, so we're going to have 5 there. We're going to have 3 radical big g's, 3 radical big g's, and that's c to the 9th, so that's going to be a 9 for -9 for that. Okay, I think we got that.
I'm looking at the numbers, trying to check it.
Okay.
Charge is 1, length is -3, time -5, area -6, volume -9, 3.
Oh, is it 3 or is it? Oh, yep. No. For some reason I read h bar looked like a 5 to me. Okay. Couldn't read my own handwriting. All right, that was my mistake.
I have the advantage of typing.
Yeah.
Okay, so why the heck would I? Okay. Why in the heck is this interesting?
It's a very good question.
What if you wanted to come along and you were interested in multiplying the Planck volume by the Planck density?
Planck volume by the Planck density.
So find those 2 rows, point at them.
Got the Planck volume, I got the Planck density. Oh, that's kind of interesting.
Yeah. So without writing on the wall, you end up adding these things together. Well, the thing is, all of your information is now in the table, and it's duplicating all your scribbles on the right. You could reconstruct all your scribbles on the right, all those formulas. These are equivalent. So you can erase all that mathy, scribbly stuff and just look at the numbers. So I'm suggesting that you actually erase that whole column.
Okay.
Yeah.
All right, let's get rid of our notation and let's look at a radicalized form of what we got going on to account for a bit of reality then.
Yeah,
Hey,
so
maybe-
now multiply the Planck density by the Planck volume using this table. So all you do is you add the numbers in column-wise.
Oh. Oh. Okay, so then if we were to do
So radical C to the 10 minus 9 power.
let me just write this out for my own
Yep.
knowledge. So we're gonna do all right. So we're gonna do the Planck density. I'm gonna multiply by the Planck volume. All right. So we got LP cubed, and then we can do that. So that will equal
Yeah, just like copy on the next
radical
line down.
radical C, which will be
Just
1.
do that one to radical C to the 10th power. Just like do a radical C,
Yeah.
and then just do the 10th power.
Yeah.
And then underneath that, write a radical C to the minus 9 power.
Okay. Yeah. To the minus 9. All right. So
Great. And now do the radical H to.
Yeah.
So first look at density, H bar. Yeah.
H bar. All right. And then we got minus 2. And then we got that. We've got, all right. We coincidentally get a 3 here. So we got radical H to the 3rd. And then we're going to have,
Radical G.
all right. So radical G minus 4. And then it's going to be radical G to the 3rd. Oh,
There
if
you
we add
go.
those
Now-
up, those equal 1.
Write a horizontal line underneath that.
Yeah.
And you're going to multiply these things by adding their exponents.
Okay.
So you do a radical C, and then what's 10 minus 9?
It's 1. Okay. Raised to the first power. We're going to do radical H. That's going to be to the first power.
Yep.
And then this is going to be radical G to the minus 1. Which, wait a second, is that radical
Yeah.
G to the minus 1? All right.
Okay. So now just write 1 and then 1 and then minus 1 underneath those things. Kind of drop those things off. Just do a 1 right there.
1,
And another 1
1,
and a minus 1.
1.
Perfect. Now
Oh.
go search your chart for a 1, 1, minus 1.
A 1, 1. A 1, 1 minus 1. Oh, look, math.
Oh, look, mass.
That's
What
very
did you
interesting.
multiply together?
Yeah, it's well, that actually makes perfect sense because that's what you would get.
If you multiply
The
density
Planck
by
density
volume.
by the Planck volume. Yes, you will get the Planck. Oh, that is cool.
Now, here's why this, well, I think it's time to do alpha.
Okay.
By the way, so what I just did is I used the law of exponents. You now have all these radical powers. And so if you want to multiply these things together, you just add the radical powers together and you've got your expression. If you're dividing,
Oh.
you're going to subtract. If you're multiplying, you're going to add.
Oh, this makes things a lot easier. I know, because a lot of times I'll construct things and I'll be like, as long as it's even powers, it's okay. I could take a square root or something, but it's like, oh, there's one odd power. What the heck do I do with this?
I want you to compare by looking at the chart, compare frequency and time.
Hmm.
You won't need to write anything. Just point at it.
Okay. All right. So we got frequency here. All right. So we got frequency. We got time. All right. So, oh, look, frequency got a 5 for the radical C. Oh, look, -5 for the radical C. Got 1 for H bar.
You
And
move
then,
your chair a little.
oh, yeah. Okay. I think I must have done this wrong because that should be, oh, wait. Hold on.
You have your finger on it, so I don't know what.
Yeah, no, that should be a -1, right? Because it should be the inverse.
Time. Oh, frequency was supposed to be a -1.
Ah. Okay, yeah. Frequency is
was supposed to be.
Oh no,
-1,
it's
-1.
right. It's it is right. It's temperature.
Oh, you were reading temperature.
No, I was just getting confused because I have terrible handwriting and I was doing a wave. Okay, so frequency is 5. Time is -5. And then for radical h bar, it's -1 for frequency. It's 1 for time. It's -1 for radical g for frequency. And then it's 1 for time. Okay, so those would net out.
So what can you say about the relationship between frequency and time?
Oh, I mean, they would equal 1, or actually they would just cancel out, right?
If you were to multiply them together, they would just cancel out, wouldn't they? So if that's the case, what does that mean mathematically?
Does that mean it's ill-defined?
No, it's not ill-defined.
Oh, actually, no, it is.
You're looking straight at the definition of both of them.
No.
You see how they relate.
I'm not sure if I like the definition, Rick, though. I'm not sure. Ooh.
How does frequency relate to time?
Cancels it out.
If you were to multiply them, it would cancel.
Yeah.
And if that's the case, if you take two numbers and you multiply them, then if you get an x to the first power times an x to the -1 power, we call that a special name. We call those an inverse.
Oh, yeah, no, yeah, oh, okay, yeah, because frequency is the inverse of time and time is the inverse of frequency.
Yeah.
Because the numbers are just direct opposites.
Yeah.
Oh.
So that's what this chart is telling you. You're looking at the chart, you're like, oh, look, time and frequency are inverted. What's the relationship between energy and temperature?
Oh, okay. All right. Yep. So energy and temperature, they're the same thing, except it's got the Boltzmann constant in it.
Yeah.
So it's the same
so anytime
thing.
you look at temperature, you're looking exactly at energy. It's just times a constant.
Yeah. Yeah.
So it's like temperature kind of obfuscates energy because it's like you're multiplying by that constant because the nature of the kind of energy the temperature is a bunch of random energy. That's what that Boltzmann constant is telling you. When the energy is randomized, there you are.
Oh. When the statisticians like to take over.
The what?
Oh, the statisticians, yeah, the stochastic processes and probability and everything. Or at least that's where I think it came from, but.
Let's do alpha. I'm just going to read off the numbers for alpha.
Okay.
Alpha has -2 square roots of c.
Yeah.
-2 square roots of h bar. The electric constant is 2.
Okay.
I have to adjust because your chart and my chart are a little different. And electric charge is 4.
Yeah.
All right. So that's, I'd like to point something out about alpha and charge. I want you to look at root G for alpha and charge. Just kind of point at them.
Okay. There's nothing there.
Nothing there.
Yeah.
There's zeros.
Yeah.
So this mechanism, zeros are implicit everywhere, like a Planck force is 0 h bars. But it's the fact that nothing shows up there tells me something really amazing about the entire universe. Is what's going on is gravity is fundamental. And all of these Planck forces and units and whatever they're doing, they're conspiring together. And the Boltzmann constant doesn't really matter. That's just our little thing. But it's really root C, root H bar, and root G are working together in order to cancel out gravity as it makes electric charge. So the charge on the electron, see that 4?
Yeah.
It's all lonesome. None of the other things have anything to do with the charge of the electron. We just have this electric charge thing, and that's the only thing contributing that 2, so that Q sub P and alpha are related, so that in order to make the 2 Boltzmann constants, you need to like invert the electric charge and then square it. And then if you're squaring an electric charge, then you get the root C and the root H also.
Yeah, because charge squared is literally like the 4 pi epsilon naught H bar C. Yeah.
But all of these other things are all working together like in some grand conspiracy.
Is it a grand conspiracy, or is it working as intended?
Well, as intended. Yeah. So this already is extremely satisfying to me.
Oh, this is wonderful, because I'd kind of looked over some of this stuff before, and I'm like, you had given me a little bit of literature, and as I was going through it, one of the things that I did notice was, at least for mass, I'm like, all right, it happened to be to the first power there, and I'm like, okay, that's very interesting. That may be suggestive of different things. I'm not particularly sure what, but it has my attention.
Yeah. So there's this thing I want to just dying to tell you. I want you to do 4 different calculations. So erase to the right the density times volume. We'll use that little space.
Yep. Okay.
We're going to do 4 problems.
All right. May I do one clerical thing first?
Righto.
Okay. So hello to the audience that I've been completely ignoring this whole time. I apologize.
You get you. I haven't looked at the chat at all.
We were like 50-50. I'm like, I could have just given Rick, I'm like, we could just record this and we can always edit it or some later. I'm like, oh, let's just do a live. So welcome to the great the Poindexter, the Rotten Piranha. We got Crypto Alchemist in the house. Yes. Hey, you can hit whatever buttons you want. I ain't the boss of nobody, but we have a premier mad scientist who, it's not necessarily a question of whether you're crazy, it's whether it's crazy enough. I happen to personally believe Rick is sufficiently crazy. My opinion. So we'll see. We'll see how things play out. So all right, we're doing some problems.
So the 4 problems in order are going to be to multiply, well, I just want to say it, MPTP, so mass times time.
All right, yeah.
Next one is MPLP.
LP.
And the next one is EP, energy, times time.
All
right. TP. And then EPLP.
All right. And then EP. Well, I'm going to need to give myself some more room to do this out. So what was the third one again, Rick?
EPTP.
P and the last one?
EPLP.
Okay, so EPLP. All right.
Start with EPTP. Okay, and don't even write it down. You just like, this is so fun.
Oh. Okay, so it's energy time, correct?
Yeah, energy time.
Okay, so energy is going to be, all right, so we got this. We have H bar radical That's going to be the first. And then big G radical. And then that's going to be -1. -1. And then time. Time is -5.
You don't, yeah, you just write your numbers down. Don't
Yeah,
worry
okay,
about
all right.
the expression.
So -5. Okay, yeah. Oh, that's the whole point of it.
Yeah.
Okay. All right. All right. So -5, 1 and 1. All right. So 1 and 1. And then I have, okay, so that's going to be 0, 2, 0.
The mad scientist smiles in anticipation. So
Zero.
EP times TP equals,
It's
you just write
H
it down.
bar. It's 2 or H bar, right? Or did I do that wrong? The sign.
So EP times TP equals sign.
Yeah.
Equals what thing?
It equals H bar according to this, right?
Yeah, there you are.
All right. All right. Huh. Oh. Oh.
Now just do the columns for the next one. Don't bother writing it down. You know you have 3 columns.
Okay. Yeah.
So do
Okay.
EPLP.
So EPLP. All right. So EP would be 5, 1, -1. And then
Underneath
we're gonna have,
that,
yeah, and then LP is -3, 1, 1, 1. So that's gonna give us 2, 2, 0. That's 2. Oh,
so your
okay.
conclusion is,
So that's gonna be 2. It's gonna be, all right. So it's gonna be C times H bar. Yeah, C times H bar.
yeah.
Okay.
So you can write that next to the EPLP equals.
E
You've shown your work.
equals C. Yep. Yep. All right. Work shown. All right. We're going to math, which is 1, 1 minus 1, 1, 1 minus 1. And then time we have here, which is, so that's -5, 1, 1. Will give us -4, 2, 0. So that's
Rockin'.
going to, all right. All right. So we're going to have C squared in the denominator, C squared
But
in the denominator. And
But
we
it's a
got
radical.
up.
Oh, no, no, no.
Oh,
you
no,
got it, you got
because
it,
it's
you got
4.
it.
Yeah, it's
You're all good.
-4. So that would be 2. So see, no, Rick, you're a good teacher. It's all right. And then that's going to be H bar over C squared. Oh, that's neat. All right. And then we have other guy. Let's move this over here just because I'm already confusing myself. So MP, LP, MP, LP. We'll just do this. So MP is 1, 1 minus 1, 1, 1 minus 1. And then LP is
Minus
3,
3, 1, 1.
1, 1. That's going to give us -2, 2, 0. So that's going to be C in the denominator. And then that 2 would be 1 H bar over C. Oh,
Look at those 4.
yeah. Okay, that seems to all add up.
Yeah.
Mass times time is H bar over C squared. Mass times length is H bar over C. Energy times time is H bar. And then energy times length is CH.
Yeah.
Oh.
So in general, you've got an H bar and C to some power, but EPTP has an implicit C to the 0th power. C to the 0th power is a 1.
Right. So C.
So point at, yeah,
C
right
to the
there.
0.
C to the 0.
That is 1.
Yeah.
Ah. Oh. Oh.
So you
Okay, I need more
have
calculation.
energy and mass and time and length all pretty much put together right here. Because mass is energy and length is time. They're all the same thing.
Oh. This is highly suggestive. I'm not sure what it's suggesting, but
It means if you talk about energy, then you're automatically talking about mass. If you're talking about space, you're automatically talking about time. They're only they're related by different powers of C, but they all have this H bar going on.
yeah. Dang. Things everywhere.
Yeah. I've been sitting on this for a long time. I'm like, world, please let me publish. So,
Oh, this is a. I mean, I don't know. Maybe someone else has been talking about. I mean, you would know better than I would, but this is
I
the
haven't
first
seen
time I've
anybody
seen
else
any
do
of this at all.
no. And there we are. You've been radically empowered.
Okay, all right. The title makes sense now. At first, I'm like, all right, he's a mad scientist. Are we going to go full Emperor Palpatine here, unlimited power or something? No. Radical power. And that's literally what it is. It's radical power.
I just wrote a Palpatine quote in my paper today.
Oh.
No, my young Jedi, it is you who will find that you are mistaken about a great many things.
Well, Jason, what's this? These are radical powers. That's a fantastic question. Basically, rather than going through all like the notation that we had here, so if you start probably about 10 minutes or so into the video, of course, this will be available for replay. Basically, Rick had me write out all the standardized formulas for all this different stuff. And then he just points out, it's like, well, if you happen to take the radicals of these things, so rather, because a lot of times you'll see something like the Planck time is like c to the 5th divided by, it's the radical of c to the 5th divided by h bar, big G, both the h bar and big G in the denominator. He's like, well, you can do all that, or you just kind of look at the table. And if you were to take the radicals of those, so rather than like c to the 5th for the Planck density, you would take the radical of that. So rather than being 5 powers, you would just take 10 powers of the radical C. So it's another perspective that seems to, at least for me, be perhaps telling in some ways, because especially when you start seeing different things like, for instance, I know it's a terrible chart. I'll have to make it prettier, but you see time and frequency. How many radical C's are in the frequency? 5. How many radical C's are in time? -5. How many radical H bars are in frequency? -1. How many are in time? 1. How many radical G's are in frequency? -1. How many radical G's are in time? 1. So basically, those net out. They're inverses of each other. And the table lays it out in a way that, to be fair, I mean, you could probably do this or teach this to kids in just grade school, or at least high school.
Yeah, it's not hard. What's high school, though, I'm sure, right?
Right. No. That's why I'm
Even
saying
in
it
undergrad.
depends. Well, if somebody has interest in it, because a lot of this, I mean, this is basically just standard high school math, and it's like, to be fair, it's actually easier than some high school math because you really just need to add.
You're really just adding, but when you're multiplying, you're just adding the exponents. This is the law of exponents being applied to make things easier. This is how the slide rules used to work. Law of exponents.
Yeah. So I have to do my due diligence. So how did you come to this?
How did
Let's go into the discussion phase. Let's
well, do you remember Archimedes' Law of Gravity?
I do. I used the same thumbnail and just called it Radical Powers because there was a nice picture of you with a board with some stuff on it.
There we
I
are.
will replace it with this.
So in Archimedes' Law of Gravity, I found a different way to write G.
Mm-hmm.
And what I found is that Newton had written his constant in the numerator, and he really should have written it in the denominator. So I thought, well, if I've got a new value for G, if I've got a new definition of it, then what if I just substitute that into the entire Planck scale? So in my paper, that's what I did. I just took all the Planck scale formulas. I said, okay, I'm just going to replace the G with my new number. And I got something I call the aquatic scale because it puts all of the Planck scale in terms of the density of water, which is one of the deepest, probably the single deepest result, because the density of water should never have gotten into the gravitational constant. There's no evolutionary path. The density of water happens on planets, but the planets have to form before the density of water can happen. But the universal gravitational constant has to exist before the planet can form, before it can make water.
So that sounds like perhaps the ultimate chicken egg conundrum, and
Yeah.
it is suggestive that perhaps the what we're looking for to explain gravity, the argument's going to have to hold water.
Yes. Yes. So I'm not going there at this time because we've certainly covered plenty today.
I mean, we're coming up on an hour. That's what we normally do. Can I show them the little interesting thing what happens when you invert big G?
I want to tell you something before our hour is up. So they can certainly watch the Archimedes Law of Gravity video. That's a more complete explanation.
Okay.
But I want to tie it to the work that Thad has been doing.
Mm-hmm.
He calls them 5 dimensions.
Mm-hmm.
What are those 5 dimensions that you guys talk about all the time?
Time, space, charge, mass, and temperature.
And you always talk about them in terms of their Planck things,
mm-hmm.
right? Well, Thad has combined those into little expressions. Each one of his constants of nature has some combination of Planck units.
Mm-hmm.
And he puts them into multiplications and divisions,
mm-hmm.
which means this technique I just showed you for the MPTP, MPLP, EPTP, EPLP, that same technique can be applied to all of Thad's work. Every one of those 288 constants has a form that's like this. And by looking at it in this form, in this table, but I lack, because I'm like in Seattle and you're in Utah and all that stuff, I don't have that level of connection with what Thad has been doing. But certainly I've been looking at it and going like, oh, look at what Thad's doing. You know, I can now
you've given me a bunch of homework. Thank you.
Right? So this is a tool for Thad to reinterpret those pieces. And he doesn't have to do all the long expressions, right? So what's interesting is how he's combined I don't like this word, but quintessence. Quintessence means something different. But you guys talk about these 5 things and sometimes use the word quintessence for it. It's not easy.
I think it was a Sean Carroll term that was initially introduced. I don't know.
Okay.
I feel like he said he introduced it. I could be wrong.
Quintessence is a pretty old word, and it's kind of an ether kind of thing, sort of.
Well, ether's
But they don't
a
want to talk
5-letter
about
word. We
Yeah.
no, space-time medium, the cosmic whatever,
No.
the vacuum, but no ether.
No ether. That certainly is wrong. You know, but Archimedes' law of gravity, this is the dodecahedron. It's 120 sides, the ultimate fair die. Here I am in my very nice living room. See that piano over there? That's my piano, right?
Wait a second. A dodecahedron. I mean, 120-sided die, but Rick, that's 5 factorial.
It is 5 factorial.
Huh.
Huh. Amazing.
It's very neat. It gets the old noggin a jogging.
Yeah. So that's plenty for today. Did you have any questions or?
I got plenty of questions, but
okay.
I think let's end it here. We can discuss some things behind the scenes, and we'll go from there. So hey, I know we threw a lot at you. I was kind of this is more of a learning scenario for me that's been documented live. So anybody else now or temporally in the future, any internet archaeologists in a millennia, if we manage not to destroy ourselves, can happily come back and see when this was said. But other than that, take care, y'all. And
one moment. I have one more thing to add.
Oh,
right now, Pacific time, it's 4:35 in the evening on Friday, April 25th, 2025.
All right. Well, I'm currently in the
That was
future
when
at
this
5:35. So, with all that said, take care, y'all, and here's for a better future. Let's level up. Oh, geez, I don't have the right shirt, but